L'Hopital's rule is a way to apply derivatives to help us evaluate limits that have indeterminate forms. So an indeterminate form is a limit of the form, say 0 over 0. As x goes to 2 here, I get 4 minus 4 over 2 minus 2, or 0 over 0. So when I see 0 over 0 in a limit, or infinity over infinity, and there's some other variations on these, L'Hopital's rule is a trick for helping us. Before, when we had something like this, we had a list of 4 different things we might try, factoring and canceling. That works here beautifully. So L'Hopital's rule is more than we need for this particular limit. But as we'll see, L'Hopital's rule will do a beautiful job. Now I can use direct substitution. I get 2 plus 2 is 4. We saw other limits that gave us indeterminate forms where we had to expand things. For instance, as h goes to 0, 5 plus h squared minus 5 squared over h. It's the sort of thing that arose when we were taking derivatives. We expand this. Common denominators was another nice trick. So if I get the numerator there on a common denominator, I can do some algebra then, the factor and cancel, and figure out what's going on with this limit, the conjugate. Okay. If I multiply the top and the bottom by square root x plus 4, we can make some progress there. But then we encountered other kinds of limits for which none of these tricks applied. One of these comes up when we're trying to find the derivatives of trig functions. Remember, this is one of our special limits. We know this to be 1, but we had to use properties of trig functions and kind of a geometric proof to show that. L'Hopital's rule gives us a way where we could evaluate this limit directly or by applying the derivative in the correct way. So this is an indeterminate form. As t approaches 0, we have 0 on the top, 0 on the bottom. What does that mean? Well, what does L'Hopital's rule say, and why does it work? All right. So this is directly from your textbook. L'Hopital's rule says that if we're looking at a quotient, right, and that quotient is of the form 0 over 0 in the limit, or it's of the form infinity plus or minus infinity over plus or minus infinity, right? Then, if this right-hand limit exists, I can instead evaluate this right-hand limit. So what does that say? It says I'm going to take the derivative of the numerator, take the derivative of the denominator, and I get a new limit. And if this limit on the right exists, then it's equal to the original limit. Right. This only works, caution here, if we're of the form 0 over 0, or plus or minus infinity divided by plus or minus infinity. If you don't have one of those forms and you try and do this, you'll frequently get a wrong result. Why does this work? Well, just a little bit of insight. Suppose I have the form 0 over 0. So I have some function f. Here it is at a. All right. At the number a, f is going to 0. We have some other function g. It's going to 0, and so as x approaches a, f over g is of the form 0 over 0. Well, what we're going to do here is linearize. So if I linearize f, I get a function of the form f of a plus f prime at a times x minus a. What's really important here is at what rate do these functions go to 0? And that's determined by the derivative. Let's call this linearization LF. The linearization for g would be g of a plus g prime at a times x minus a. And what we're going to do is substitute those linearizations into the limit and see what it might do for us. So we have the limit as x approaches a of f of x over g of x. 0 over 0 in the limit. So this is equal to the limit. We're going to replace the functions with our linearizations. If the function is differentiable, then very near to a, L, and the function and its linearization are going to be in good agreement. This is not technically a detailed proof, but it'll give you some idea of what's going on here. Let's put in our formulas for those linearizations. Remember, linearization is just finding the equation of the tangent line. Now in this scenario, remember, f is equal to 0 at a. G is equal to 0 at a. So this is 0 and this is 0. So I'm just going to rewrite that. Now you can apply L'Hopital's rule without really understanding what's going on here, but this just gives you some idea what's up. I can cancel these now. Alright. F prime of a is just a number, G prime of a is just a number, so direct substitution essentially, and I get this. Right. And if f prime and g prime were continuous functions, that would be the same as that limit. Right. So this gives you some idea of why we can use L'Hopital's rule. All right. When f and g are both 0 at a, right, then what matters is the slopes, the ratio of the slopes. All right. And that's what L'Hopital's rule says we have to do, is take the limit of the ratios of the slopes. All right, let's look at a lot of examples now. This first one is one for which we don't really need L'Hopital's rule, but we're going to do it anyway. All right. The first thing you need to check is that when you plug in, when you try direct substitution, you have an indeterminate form. When I plug in 2 here and do the numerator, I get 0, 0. So this is certainly of the form 0 over 0. It's an indeterminate form. And according to L'Hopital's rule, I like to write a little LR to remind myself that's what we did there. I take the derivative of the top, and I take the derivative of the bottom. This is the only place where we get to sort of use this naive form of differentiation, where we take f over g and we, in some sense, replace it by f prime over g prime. That doesn't work anywhere else, and here it only works when we're working with limits. We're never ever going to have f over g prime is the same as f prime over g prime. That's a nonsense rule. It works for limits with L'Hopital's rule, but it doesn't work otherwise. Now, after applying L'Hopital's rule, f over g, the limit as x approaches 2 of f prime over g prime, I can simply evaluate here. So I get 2 times 2 plus 1 over 1 or 5. Now, you didn't need L'Hopital's rule to do this one, but let's write it again and just see it without. L'Hopital's rule is a nice trick when it works. Here I can factor and cancel. I did not need L'Hopital's rule to begin with. Now direct substitute, 2 plus 3 or 5. Alright, let's look at one where L'Hopital's rule is truly useful from the beginning. I can't really do it. Well, you could do it with some other special tricks, but L'Hopital's rule will make this easy. Sine of 0 is 0, tangent of 0 is 0, so I have an indeterminate form, 0 over 0. We're going to try L'Hopital's rule. So I get to take the derivative of the top. Remembering my chain rule, I get cosine 4x times 4. Derivative of the bottom, secant squared 5x times the derivative of the inside, 5. The 4 and the 5 I can factor outside the limit. And now I'm done because I have something I can use direct substitution. Cosine of 0 is 1, secant of 0 is 1, so this is 4/5 times 1 over 1 squared, or simply 4/5. I'm going to show you what happens here if you forget to check to see if L'Hopital's rule applies to begin with. All right. So if I just jump in here and start doing L'Hopital's rule, on the top I get minus cosine of theta. On the bottom I get, let's see, minus cosecant theta times cotangent of theta. All right, let's use trig identities to clean this up. Of course, I can cancel the minus signs. I'm going to expand the bottom here in terms of sines and cosines. Cosines cancel. I've got 1 over sine squared in the denominator. Invert and multiply. I want you to keep in mind that everything we're doing here is nonsense, and we'll say why in a second. And sine of pi over 2 is 1, so this is 1 squared. Alright, is that right? Let's do it without L'Hopital's rule. Just do it directly. Direct substitution works just fine here. If I plug in pi over 2, I get 1 minus sine pi over 2. Alright, that's a little bit of a problem, but not really. Alright, I'd have 0 up here because sine pi over 2 is 0. But I have 1 downstairs. So this is 0 over 1, or 0. This was never an indeterminate form. And if it's not an indeterminate form, you can't do L'Hopital's rule. Very first thing you need to check is if I plug in here, do I have a limit of the form 0 over 0 or infinity over infinity? If you don't, then stop. L'Hopital's rule doesn't work. Here's an example which illustrates how sometimes we have to use L'Hopital's rule repeatedly in order to get the answer. As x goes to 0, tangent 0 is 0, so I have 0, 0, 0. Everything is 0 over 0, indeterminate form. Apply L'Hopital's rule. Take the derivative of the top, take the derivative of the bottom, reassess the limit. Right. As x goes to 0, secant squared is 1, so 1 minus 1, 0 on top, 0 on the bottom. L'Hopital's rule again. Now things get a little bit ugly, but we have to do the chain rule here. We've got secant squared, so we get 2 times secant of x to the 1 power times the derivative of secant x, which is secant x times tangent x, minus the derivative of 1, which is 0, all over 6x. So I've got 2/6 or 1/3 secant squared x tangent x over x. As x approaches 0, I've got a 0 in the denominator, and I have a 0 in the numerator. So we've got 0 over 0 again. Now you could use some of the special trig limits we had before, or you can use L'Hopital's rule yet again. So let's take the 2/6 out as 1/3. All right, you gotta use the product rule here. Secant squared, we just saw that was 2 secant x tangent x. So that's the derivative of the first. Leave the second alone. Plus leave the first alone. Times the derivative of the second. All divided by the derivative of the denominator, 1. And this looks simply awful, but let's clean up a little bit. This is no longer indeterminate because I've got a 1 in the denominator. Now as x goes to 0, tangent goes to 0. So we've got the 1/3 times 0 plus secant of 0 is 1. So the answer is 1/3. So sometimes it's necessary to use L'Hopital's rule repeatedly. Alright, let's look at a limit of the form infinity over infinity. Right. We learned to deal with these kinds of limits involving an infinity back in chapter 3. There we divided through by the highest power term in the denominator, so x squared. We're also going to look here to see how L'Hopital's rule could apply to this limit. As x goes to infinity, we have infinity in the numerator, infinity in the denominator, so infinity divided by infinity. L'Hopital's rule isn't necessary here, but it does a beautiful job. And it will apply to other limits, as in our next example, where the divide through by the highest power term doesn't work. So we're going to differentiate the top, differentiate the bottom. Still of the form infinity over infinity if you don't feel like simplifying. So we'll do L'Hopital's rule again. Derive the top, derive the bottom. 2 over -4 or -1/2. And if you look back here, that's the same as the leading coefficient, 1 over -2. But that trick didn't work all the time, dividing through by the highest power term. Let's look at this guy. It should just be u over 10. Right. So as u goes to infinity, e to the u goes to infinity, and u cubed goes to infinity. Now you may remember back from chapter 3 that we said exponentials grow a lot faster than polynomials. So the value of this limit is going to be infinity, but let's show it using L'Hopital's rule. Differentiate the top. Derivative of e to the stuff is e to the stuff times the derivative of the inside, derivative of the bottom, straightforward. I'm just factoring out the constants. L'Hopital's rule applies again because we still have infinity over infinity. Forgot the constants up front. They won't matter in the end here. Still infinity over infinity. We gathered up the constants again up front there, so that was L'Hopital's rule. I'm just cleaning up now. One more time with L'Hopital's rule, and we'll be done. So clean up one more time. As u goes to infinity, e to the u, or e to the u over 10, doesn't matter, goes to infinity. So 1 over 6,000 times infinity, pretty much infinity. This next example is an example of what's called an indeterminate product. Doesn't fit our L'Hopital's rule form exactly, right? But we can make it very easily into one that does fit our form. Okay, so as x goes to infinity, square root x is going to infinity, but e to the negative x over 2, that's exponential decay, goes to 0. So something very large times something very, very tiny, what does that mean? So this is an indeterminate form. The trick here is to write this in a different form where we can apply L'Hopital's rule. And to do that, we're just going to use rules for negative exponents in this case. And now I have infinity over infinity, so L'Hopital's rule applies. And if you're on your game here, you'll notice here, square root doesn't grow very fast. Exponential growth whomps the square root, and we get 0 in the limit. But let's actually show it. Derivative of the top, derivative of the bottom. Okay. So now the fractions are kind of a mess, but when we take the derivative of square root x, we get x to the minus 1/2, right, which in the denominator. So here it is in the denominator. Now as x goes to infinity, we have infinity times infinity, and that is definitely big. So 1 over infinity, 0. That was an indeterminate product. Let's look at another one. As x approaches infinity, tangent of 1 over infinity, tangent of 0 is 0. So again, we have infinity times 0, an indeterminate product. The trick here is, we want to write this in the form that L'Hopital's rule applies, is to take x and rewrite it as 1 divided by 1 over x. Kind of crazy, but it works. So this first step is just rewriting. Invert and multiply that bottom x, and you're back to multiplying by x. L'Hopital's rule works great here. Tangent of 1 over infinity, 0. 1 over infinity, 0. So this is the form 0 over 0. We're going to differentiate upstairs and downstairs. Derivative of tangent of some stuff is secant squared of the stuff times the derivative of the inside. X to the minus 1 gives us 1 over x to the minus 2. Or minus 1 times x to the minus 2. So we should have a negative here. Derivative of the bottom, minus 1 over x squared. Cancel, cancel. Secant squared 1 over x. As x goes to infinity, we've got secant squared of 0, which helpfully is 1. All right, just a couple of examples remaining here. This is an example of what's called an indeterminate, what do you want to call this, exponent? All right, here we've got as x goes to 0, 0 to the 0. What does that mean? All right, it's one of a variety of indeterminate forms. When you see 0 to the 0, we know that like 3 to the 0 is 1, but what does 0 to the 0 mean? Or infinity to the 0, so the base is growing very large while the exponent is growing very small. Or 1 to the infinity. The one of these things that is not an indeterminate form is 0 to the infinity. That just works out to be 0. So we don't need that. We don't need L'Hopital's rule in that circumstance. But we do need a trick here. And the trick here is similar to the trick we used when we did logarithmic differentiation. Right? If I have f of x raised to the g of x power, that's the same as saying e to the natural log of f to the g. I've taken off the of x's just for simplicity. E to the g natural log of f. So we're going to take this guy and write it as, and that doesn't appear to help, but we'll see where this goes. Right. E to the natural log of x to the x is the limit as x goes to 0 from the right of e to the x natural log of x. And now look at this. We've got, ignoring the e for a moment, x is going to 0. Natural log of x is going to minus infinity as x gets close to 0 from the right. So this is an indeterminate product here. Since e is a continuous function, I can write this as e to the limit as x goes to 0 plus of x times the natural log of x. So what I need to worry about is this guy. Let's just call this e to the L. Right? Where L is the limit as x goes to 0 from the right of x natural log of x. Alright, this is an indeterminate product and we can deal with this. We're going to rewrite it by taking that x from the numerator and writing it as 1 over x in the denominator, just like we did in the previous example. Now L'Hopital's rule applies. Derivative of natural log of x is 1 over x. Derivative of x to the minus 1 is minus 1 x to the minus 2. Clean up that fraction. Should be as x goes to 0 from the right. Right. So the value of the limit L is 0. But remember here we need e to the L. So our original limit we said was equal to e to the L. Our e to the 0 is 1. Let's look at one more of these. This one's the same idea. It just gets uglier. So we're going to use our e to the natural log trick. Alright, so we need to understand what happens to this. Alright, so we'll just say that this is equal to e to the L, where L is equal to the limit as x goes to 0 from the right of x natural log of tangent 2x. Going to rewrite that in a form that where we can apply L'Hopital's rule. Differentiate the top and bottom. One over tangent 2x. Derivative of log of some stuff is 1 over the stuff times the derivative of the inside. Now applying the chain rule, we get another 2. Right, so that's a double chain rule for the numerator. This doesn't appear to have been helpful, but if I clean up, still doesn't look helpful. Let's try taking these trig functions and replacing them with sines and cosines. Maybe that'll get us somewhere. Should be secant squared of 2x. Now if I invert and multiply, I can cancel off one of these 2x's. Probably should have just changed to sines and cosines right at the beginning. But sometimes you don't see these things until you get into it. So we're inverting and multiplying the denominator. This one's kind of ugly. Alright, you can either use special trig limits or you can do L'Hopital's rule again here. A really nice trick. When you see cosine of theta times sine of theta, that's the same as 1/2 sine of 2 theta. That's just a rewrite of the double angle formula. Now, if you didn't see that, you could apply L'Hopital's rule here. Be careful using the product rule for the denominator. Now we're going to do L'Hopital's rule one more time and be done with this guy. Derivative of the bottom is 1/2 times the cosine of 4x times derivative of the inside, which is 4. I don't really care anymore because I can direct substitution in here. Get minus 4 times 0 over 1/2 times 4 is 2 times the cosine of 0, which is 1. So we have 0 over 1, or minus 4 times 0 over 2, but that's still just 0. Now remember, in the beginning, that's the value of the exponent. To evaluate the whole limit, we needed e to the L, so that's e to the 0, or just 1. So that shows the value of our original limit. That one's messy. Last example. This is an example of what's called an indeterminate difference. Right. As x gets close to 0, remember cotangent is cosine of x over sine of x. So as x gets close to 0, we're dividing by sine x here. So 1 over 0 is infinity, minus 1 over 0, infinity. So we have here, this is the form infinity minus infinity. Now the trick is to change that into a form where we can do L'Hopital's rule. Right. What we're going to do is rewrite this and then get a common denominator. Now from here to here, that's just getting a common denominator. So if you didn't see that, we're going to take and multiply by x over x and sine x over sine x, and then combine. As x goes to 0, I've got 0 minus 0, so we have 0 in the numerator, 0 in the denominator. We can do L'Hopital's rule now. This is now of the form 0 over 0, whereas before we had infinity minus infinity. Right, this is a bit messy, but doable. We're going to use the product rule here. Then the derivative of minus sine x is minus cosine x. Product rule for the denominator. Cosine x minus cosine x, they cancel. I'm just going to rewrite this for clarity. This looks pretty similar to where we started just a moment ago if you compare this guy and this guy. But one more application of L'Hopital's rule and we're going to be home free. Why does it apply? Well, I have a 0 here, 0 plus 0. So we're still in the form 0 over 0. Indeterminate, try again. Take the derivative of the top, take the derivative of the bottom. That minus sign multiplies everything, so we're using the product rule here. A little cleanup. Not much to do upstairs. Downstairs, not too much. But now look at what happens when we plug in 0. We can direct substitute. We get minus 0 plus 0. Sine of 0 is 0. Minus 0 plus 2 times the cosine of 0, which is 1. So this is negative 0 over 2. Well, negative 0, of course, is just 0. 0 divided by 2 is still 0. So finally, in this last step, we went to something that wasn't indeterminate. We've got 0 over 2. Right? And that's definitely 0.